Welcome to the Sleepy Astronomer. I'm so glad you've joined me tonight. Let the noise of the day drift away and the stillness of the cosmos take its place. As you settle in, imagine the quiet before everything began, before light, before time itself. Tonight, we'll journey back to the moment the universe took its very first breath, the beginning we now call the Big Bang. If we look into the cold, clear night sky, filled with stars scattered across an immense black canvas, we are not just seeing light, we are looking back in time. The further out we gaze, the further into the past our vision carries us. This remarkable truth lies at the heart of one of the most profound ideas in science: the Big Bang. The Big Bang is not an explosion in space, as the name might suggest. It is an expansion of space itself. It tells us that the universe had a beginning, a moment roughly 13.8 billion years ago, when all the matter, energy, space, and even time we know today blossomed from an unimaginably hot and dense state. It is a theory not born from idle speculation, but forged from careful observations, mathematical insight, and the relentless curiosity that drives science. Before the Big Bang theory was widely accepted, many believed the universe was eternal, unchanging on the largest scales. It seemed more comforting, perhaps, to imagine that the cosmos had always existed just as it is now. But the universe holds no obligation to our comfort. It tells its story through data, through the faint glow of ancient light, the movement of galaxies, and the elemental mix written across stars. At its core, the Big Bang theory provides a framework for understanding everything we see today. From the structure of the vast cosmic web stretching across billions of light years, to the smallest atom inside our own bodies, all trace their origins back to this singular beginning. The theory explains not just how the universe began, but how it evolved, why galaxies formed, how stars ignited, and where the elements that make up planets and life. By rewinding time and tracking the expansion of space backward, we find that the universe was once far smaller, far denser, and far hotter. In its earliest fractions of a second, temperatures were so extreme that matter, as we know it, could not exist. There were no atoms, no nuclei, not even protons or neutrons. The universe was a seething plasma of pure energy, governed by physics we are only beginning to understand. From that initial fireball, the universe has been expanding and cooling. Over time, energy condensed into matter. The simplest elements, hydrogen, helium, trace amounts of lithium, formed in the brief moments after the Big Bang. These became the raw material for the stars, which in turn forged heavier elements in their fiery cores. Over billions of years, those stars gathered into galaxies, and within those galaxies, planet systems emerged. On at least one of those planets, life arose and began to ask these very questions. Understanding the Big Bang reshapes our view of existence. It tells us that the cosmos is not static or eternal, but dynamic and evolving. It opens a path of inquiry that connects the largest clusters of galaxies to the tiniest particles, from the quantum foam of the Planck era to the curvature of space-time itself. Crucially, the Big Bang doesn't just offer a story, it makes predictions. It defines a set of conditions we should observe if the theory is true, and time and again, those conditions have been confirmed. We expected to find a faint afterglow from the hot early universe. And we did. The cosmic microwave background, a relic light bathing all of space, whispering messages from the past. We expected to see galaxies drifting apart, and we observe exactly that through their redshift. We expected certain ratios of light elements, and stars across the cosmos bear witness to these ancient alchemies. Yet, for all it explains, the Big Bang is also a frontier. it brings us to the edge of understanding, to a moment beyond which our current physics begins to break down. At the very earliest times, in those tiniest fractions of a second, space itself may have behaved in ways utterly different from what we see today. Quantum processes may have governed the universe at scales we cannot yet probe. That opens the door to new theories, new ideas like cosmic inflation, higher dimensions, and perhaps even the tantalizing possibility of a multiverse. Still, the value of the Big Bang Theory is not only in the questions it answers, but also in the grand questions it lets us ask. If everything emerged from a single instant, what lay beyond it? Why did it happen at all? What laws, if any, determined its properties? These aren't always questions science can fully answer, but they are questions it allows us to frame, to examine, and to seek through observation and thought. We are, in many ways, the universe thinking about itself. Born from stars, shaped by cosmic forces, and gifted the capacity to understand our place in the vastness of space and time. The Big Bang is not just a theory about the past, it is a lens through which we glimpse the underlying structure of all reality. With it, we journey into the deep past, move through epochs unimaginably distant, and find in that journey both knowledge and awe. For much of human history, the cosmos was thought to be eternal, unchanging, and still. Civilizations looked skyward and saw permanence. The stars rose and set in predictable patterns. The planets wandered across the heavens, yes, but within a celestial clockwork that seemed fixed by design. Aristotle, in the 4th century BCE, imagined a geocentric universe, where Earth sat proudly at the center, surrounded by nested crystalline spheres carrying the stars and planets. His cosmos was ordered and eternal. There was no beginning, no end, only continuity. This idea persisted for centuries, woven into the medieval worldview. When Copernicus proposed a heliocentric model in the 16th century, placing the Sun at the center instead of the Earth, the structure of the cosmos changed, but its eternal nature did not. Even Isaac Newton, whose laws of motion and universal gravitation revolutionized physics, continued to assume a static and infinite universe. For Newton, the universe was vast and boundless, filled with stars extending forever in all directions. It was infinitely old, infinitely large, and stable. Or so it seemed. But Newton's cosmos contained seeds of contradiction. An infinite distribution of matter would be gravitationally unstable. If mass were truly spread evenly across an endless space, gravity should pull everything inward upon itself. Yet that collapse never seemed to come. To resolve this, Newton imagined a perfectly balanced cosmos, where the gravitational pull on any point in space was exactly cancelled by matter on the opposite side. It was a delicate symmetry, one that seemed implausible even to him. In the early 20th century, new ideas began to emerge. Telescopes grew stronger. Our understanding of physics deepened. Albert Einstein, in seeking a unified description of gravity and motion, developed the general theory of relativity. It reimagined space and time as part of a single fabric, curved and distorted by mass and energy. Einstein applied his equations to the entire universe and found something startling. The equations did not naturally describe a static cosmos. Instead, they suggested that the universe should be either expanding or contracting. Einstein, influenced by prevailing beliefs, was troubled. A dynamic universe contradicted the view held by scientists and philosophers alike. To preserve a steady-state universe, he introduced a modification to his equations, the cosmological constant. This extra term would produce a repulsive force, balancing gravity and allowing the universe to remain static. It was a mathematical fix, elegant in its intent, but physically unmotivated. There was no observed force in nature matching the cosmological constant. Einstein later called it the greatest blunder of his career, though the term would resurface decades later in the context of dark energy. Even with Einstein's adjustment, the idea of a timeless, unchanging universe was being quietly challenged by other minds. Among them was the Russian mathematician Alexander Friedmann. In 1922, Friedmann began exploring the unmodified equations of general relativity. He showed that the universe naturally expands or contracts, depending on its initial conditions and energy content. Crucially, Friedmann's solutions did not require a cosmological constant. They implied a dynamic universe, potentially with a beginning in time. His work, though initially dismissed, hinted at a far more dramatic story written into the mathematics of space and time. In parallel, a Bilzen priest and physicist named Georges Lemaitre independently reached similar conclusions. Lemaitre proposed that the universe began from a single, dense point, what he called the primeval atom. From there, it expanded, giving rise to the space and time we experience. His idea was bold and metaphysical in its implications. It collided with the entrenched belief in cosmic permanence. But Lemaitre had support where it mattered most, in the physics. His models were consistent with general relativity. They made predictions. They could be tested. Still, in the absence of observational evidence, these ideas remained speculative. The sky, to the unaided eye, looked no different than it had for millennia. Stars burned steadily. The space between them appeared calm, eternal. Yet, in the decades to come, this apparent tranquility would be shattered by a series of discoveries, most notably those of Edwin Hubble. But even before Hubble's observations, the stage was set. The static universe, long assumed and fiercely defended, was showing fractures. The mathematics of relativity refused to sit still. The logic of gravity on cosmic scales led to instability. The very laws of physics were whispering of a universe that had not always been here, one that had changed, one that perhaps had a beginning. And so, by the early 20th century, the notion of a permanent cosmos stood on uncertain ground. Ideas that once seemed wild, that the universe had a birth, that it evolved, that it might one day end, were entering the scientific conversation. What remained was the evidence. It would soon arrive, carried not by theory, but by light, traveling from the distant reaches of space and time. In the early decades of the 20th century, astronomers believed the universe was static and eternal. The stars were thought to hang in place, shining sedately in a cosmos that had no beginning and no end. But this picture of the universe would not survive the observations made by a quiet revolution unfolding on the mountaintops of California. At Mount Wilson Observatory, Edwin Hubble peered through the 100-inch mirror of the Hooker telescope. It was, at the time, the most powerful telescope in the world, standing like a sentinel to the stars. With it, Hubble studied the faint smudges of light that peppered the night sky, objects once believed to be mere clouds of gas within our own Milky Way. But Hubble's diligent observations revealed a staggering truth. These were not clouds, nor stars within our galaxy. They were galaxies themselves, vast island universes, each containing billions of stars and lying far beyond the Milky Way. This was already transformative. The universe, once thought small and local, was now unimaginably vast. Yet Hubble's most profound discovery was just ahead. By measuring the light from these distant galaxies, Hubble noticed something remarkable. Their light was stretched toward the red end of the spectrum, a phenomenon known as redshift. This redshift was not random. Hubble compared the distances of the galaxies, calculated using the relationship between a star's brightness and its intrinsic luminosity. and found that galaxies farther away displayed greater redshifts. This led him to an astonishing conclusion. The universe was expanding, and every galaxy was moving away from us. The redshift of light, first described in the context of sound waves by Christian Doppler, is a simple yet powerful concept. When a source of light moves away from an observer, the light waves are stretched. Stretching increases their wavelength, shifting them towards the red part of the spectrum. It's the cosmic equivalent of hearing the falling pitch of a retreating ambulance siren, applied not to sound but to light, and not across city streets, but across the yawning void between galaxies. Hubble plotted his data, velocity against distance, and found a linear relationship. This became known as Hubble's law. The farther away a galaxy is, the faster it appears to be receding. This observation was the first empirical evidence that the universe is not static, but dynamic, changing, and expanding over time. Now, Hubble did not initially interpret this as evidence of a universe that began from a single point. That insight would come later. But his findings opened the door. Suddenly, the idea of a cosmological history made sense. If everything is moving apart now, then in the distant past, everything must have been closer together. Wind back the cosmic clock, and you approach a time when the entire universe was concentrated in a single, unimaginably dense point. This idea would become the foundation of what we now call the Big Bang Theory. The implications of Hubble's work were profound. The universe was not a changeless stage on which the cosmic drama played out. Instead, it was a dynamic entity, stretching and swelling with every passing moment. The galaxies are not flying through space like exploding shrapnel. Rather, space itself is expanding, carrying the galaxies with it, like raisins in a rising loaf of bread. This was a radical shift in human understanding. For the first time, we had evidence that the universe had a history and, possibly, a beginning. Hubble's redshifts became a window into that story, an echo of motion recorded in starlight across billions of years. Even more astonishing is that this expansion is not something confined to the distant past. It is ongoing. Every second, every heartbeat, the fabric of space stretches a little more. Light from distant galaxies travels across that expanding sea, stretched thinner and redder as it journeys toward us. And we, observers on a small planet circling an average star, are privileged to witness the silent motion of galaxies as they drift ever farther apart. Today, we can look through telescopes more powerful than Hubble's, and we see galaxies with redshifts so vast that their light has taken over 13 billion years to reach us. We are seeing them not as they are now, but as they were in the youth of the cosmos. Their starlight carries not only information about where and how they existed, but it also tells us how space itself has changed since. Hubble's discovery was a turning point, not only in astronomy, but in our understanding of existence itself. It substituted the idea of an eternal, immovable cosmos with a living universe, one that evolves and flows with time. It placed us not at the center of a completed creation, but within a story that is still unfolding. In the shifting wavelengths of starlight, we learned that the universe is a journey, and Hubble's redshifts were the first whispers of a beginning. In the early years of the 20th century, the universe was thought to be eternal and unchanging, a great celestial clock ticking steadily through infinite time. Space was considered a fixed stage upon which all matter moved, following the familiar laws of Newtonian physics. But this view would soon be overturned by a quiet revolution in thinking, sparked by a German-born theoretical physicist named Albert Einstein. In 1915, Einstein unveiled his general theory of relativity, a set of field equations that redefined our understanding of gravity. Gravity, he argued, arose from the curvature of space-time itself. Massive objects bend the fabric of space and time, like a heavy weight pressing into a rubber sheet. Planets, moons, and stars follow the straightest paths they can, called geodesics, through this curved geometry. To grasp that idea is to arrive at a stunning realization. Space is not merely a backdrop to the universe. Space and time are dynamic and active, shaped by the matter and energy they contain. At first, Einstein himself did not see the full implications of his new theory. He was convinced the universe must be static and eternal, and so he added a term to his equations, the cosmological constant, to counteract the gravitational pull of matter and hold the universe in balance. But his own mathematics resisted that fix. In fact, built into the fabric of general relativity was a deeper truth. The universe could expand or contract. It was not fixed at all. In the 1920s, independent thinkers began to explore Einstein's equations in this light. Russian mathematician Alexander Friedman was among the first. He showed that once the assumption of a static universe was dropped, general relativity allowed for an evolving cosmos. The solutions to Einstein's equations describe universes that stretched and changed with time. Others, including Belgian physicist Georges Lemaitre, would soon reach similar conclusions. Lemaitre even proposed that the universe began from a single point that expanded outward, a bold precursor to what we now call the Big Bang. Einstein was skeptical of these dynamic models at first. He dismissed Friedman's proposal, and when Lemaitre presented his ideas in person, Einstein is said to have remarked, "Your calculations are correct, but your physics is abominable." Yet, that would change. In 1929, American astronomer Edwin Hubble made an astonishing discovery. By studying the redshift of light from distant galaxies, he found that these galaxies were racing away from us in every direction. The universe, it seemed, was not static after all. It was expanding. The very fabric of space was stretching outward. Faced with this evidence, Einstein revised his opinion. He discarded the cosmological constant and accepted that his theory, as strange as it was, had predicted the truth all along. He called the original edition of the constant his greatest blunder. General relativity had revealed a dynamic, evolving cosmos. More than a century later, general relativity remains the foundation of modern cosmology. It describes how the universe behaves on the largest scales, from the birth of galaxies to the propagation of light across billions of light years. It has passed every observational test, and its predictions continue to shape our view of the cosmos. Einstein's equations are elegant yet formidable. They represent a delicate interplay between matter, energy, and the geometry of space-time. Given a distribution of matter and energy, the equations describe how space-time will bend in response. And that curvature, in turn, guides the motion of matter. Gravity becomes a conversation between mass and geometry, a kind of cosmic choreography, unfolding over the grandest of scales. At the heart of general relativity lies a deeper idea, that space and time are not separate things. They are woven together into a single, four-dimensional continuum. Events occur not merely in space and time, but within space-time. When the Big Bang occurred, it was not an explosion in space. It was the rapid expansion of space itself, carrying matter and radiation outward within the framework shaped by those same equations. One of the most profound consequences of Einstein's theory is the notion of black holes. These are regions where the curvature of space-time becomes so extreme that nothing, not even light, can escape. Predicted by general relativity and confirmed by generations of observation, black holes are among the most powerful and enigmatic phenomena in the universe. But perhaps the most far-reaching consequence of general relativity lies in how it enabled cosmologists to ask questions that were once thought metaphysical. Where did the universe come from? What is its shape, its ultimate fate? These are not just questions for philosophers. Armed with Einstein's equations and precise instruments, astronomers can now look back across cosmic history, tracing the evolution of the universe from its earliest moments. And so, the framework provided by general relativity continues to guide us. It laid the mathematical foundation for the expanding universe, predicted gravitational waves, and supports modern models of cosmic inflation. It drives the simulations that map the formation of galaxies, and it plays a central role in the search for a unified theory of physics. What began as a theory of gravity became something more, a revelation about space, time, and the deep structure of reality. General relativity taught us that the universe is not static, not eternal, but dynamic, evolving, and deeply interconnected. Through Einstein's eyes and equations, we have come to see the cosmos not as a clockwork machine, but as a living and ever-changing wonder. In the early 20th century, when most scientists still pictured the universe as timeless and unchanging, a young Belgian priest and physicist named Georges Lemaitre imagined something different. He looked at the equations of general relativity, Einstein's great revolution in physics, and he saw not stasis, but motion, not eternity, but genesis. Lemaitre dared to suggest that the cosmos was not static at all, but expanding. If that were true, then at some point in the past, it must have been smaller, much smaller. With quiet boldness, he proposed that the entire universe had once been contained in a single, incredibly dense point, a primeval atom, as he called it, and that it exploded outward in a moment of profound creation. He was a man of faith and of science, believing without contradiction that understanding nature more deeply was a path to understanding the whole of creation. Where others saw mystery, he found a call to ask better questions. His primeval atom was a startling notion, a universe born not in quiet, but in a fireball of incomprehensible energy. As time passed, stars and galaxies would form, but at its beginning, the universe was a soup of particles and radiation, far from stable. Lemaitre's insight was that this beginning followed not just from theology, but from physics. The math led there. General relativity pointed the way. At first, many scientists found his ideas too speculative. The dominant view of the cosmos was still one of fixity and eternity. Even Einstein himself was deeply reluctant. He introduced a new term, the cosmological constant, designed not to explain a moving universe, but to hold it in place. When Lemaitre showed him the implications of his own equations, Einstein reportedly told him, "Your math is correct, but your physics is abominable." It would take more evidence and more minds open to change before the idea gained traction. The term Big Bang was not Lemaitre's own. Ironically, it began as a joke. In a 1949 broadcast for the BBC, the British astronomer Fred Hoyle, a defender of the competing steady-state theory, used the phrase to mock the idea of a universe born in a single cataclysmic moment. He meant it as a dismissal, a cartoon of Lemaitre's hypothesis. But sometimes, words find their own trajectory. The phrase caught on, and it stayed. Over time, the Big Bang would become the shorthand for a cosmological framework that reached back to the very origin of space and time. Lemaitre did not seem bothered by Hoyle's mockery. He was not a man in pursuit of fame or conflict. He continued his work, quietly refining the mathematics, delving deeper into the implications of an expanding universe. He understood that if cosmic expansion were real, then the universe had a history, a story with a beginning. That concept alone was revolutionary. It turned cosmology into a narrative science. Once scientists accepted the premise of expansion, they could explore what the early moments were like, the first seconds, the first minutes, the birth of light and atoms. Lemaitre's vision formed the bedrock on which later theories would be built. Over the decades that followed, observations would confirm his brilliance. Hubble's measurements of redshift, revealing that galaxies are receding from us in all directions. The discovery of the cosmic microwave background radiation, a faint afterglow of the primeval fire. The ratio of hydrogen to helium, a signature of the universe's earliest chemistry. All of it pointed back to a hot, dense origin. All of it pointed to the Big Bang. Yet Lemaitre's cautious humility, it remains a reminder that we do not merely collect data, we interpret it. He believed that science is not just a tool for measurement, but a lens for meaning. That the universe is not only expanding, but evolving. And that with each new insight, we draw a little closer to grasping the structure beneath the stars. In his later years, he witnessed the rise of the very theory he had first imagined. He lived long enough to hear of the cosmic microwave background's discovery in the 1960s, a piece of evidence he had predicted decades prior. He did not speak loudly, but his voice echoed through the corridors of modern cosmology. And though his name is sometimes lesser known than Einstein or Hubble, in the grand story of the cosmos, few figures are more pivotal. The Big Bang theory was not born in an explosion of noise, but in whispers of understanding, steady and quiet. It began with equations, with logic, with the courage to follow implications through to their most astonishing conclusion, that the universe, all of it, had a beginning. It is one of the greatest intellectual achievements in human history. Not because it answers everything, but because it invites us to look deeper. Because it tells us that from the smallest seed of an idea, our entire cosmos unfolded. In the dark silence that followed the birth of the universe, a faint glow remained. It was not light in the way we know it. There were no stars, no galaxies, and certainly no life to witness it. Yet this glow, this faint microwave whisper, would echo across time. We call it the cosmic microwave background radiation, or CMB. And it is one of the most profound pieces of evidence we have to understand the birth and growth of the cosmos. The cosmic microwave background was first discovered by accident in the year 1965. Two radio engineers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey. They had set up a large horn-shaped antenna to investigate signals from satellites. But something kept getting in the way. A persistent noise, faint but constant, appeared no matter where they pointed the antenna. At first, they suspected technical interference. Even pigeon droppings inside the antenna were blamed. But after ruling out every possible source, they showed that the noise came from beyond our galaxy. It appeared to be coming from all directions equally, a uniform signal that enveloped the entire sky. Unbeknownst to them, a group of physicists at Princeton University had been searching for just such radiation. The Princeton team, led by Robert Dickey, had predicted that if the universe began as a hot, dense fireball, a theory then still not universally accepted, then some of that heat should remain. As the universe expanded and cooled, the intense energy of the Big Bang would dim, stretching its light into the microwave portion of the spectrum. When Penzias and Wilson described their results, the significance became clear. They had found the afterglow of creation itself. The cosmic microwave background is light, but not like the light we see from the sun or distant stars. It is microwave radiation, deep in the non-visible part of the electromagnetic spectrum. At the time it was released, around 380,000 years after the Big Bang, It was blinding, intense, and hot, about 3,000 degrees Kelvin. But over nearly 14 billion years, the expansion of space has stretched that radiation to longer wavelengths and cooled it to just above absolute zero. Today, the CMB has an average temperature of about 2.73 degrees Kelvin. Still, it fills the universe. Every inch of space is soaked in it, a silent testimony to its fiery origins. What makes the CMB so important is not just that it exists, but what it reveals. It tells us that the universe was once much hotter and denser than it is today. It confirms that the early cosmos was filled with a glowing plasma of particles and light, so hot that atoms could not form. Photons, the particles of light, were trapped, constantly colliding with free electrons and protons. But as the universe expanded, it cooled and eventually reached a temperature low enough for electrons to combine with protons and form neutral atoms. This event is called recombination. With the electrons bound into atoms, photons could finally travel freely. The universe became transparent. That first light has been flying through the cosmos ever since, redshifted by the expanding universe, until today we detect it as a faint microwave signal. It is the earliest image we have of the universe, frozen in time and bathed across the sky. Yet the most remarkable aspect of the cosmic microwave background is not its uniformity, but its slight imperfections. When satellites like SOBER, WebUMap, and Planck later mapped the sky in exquisite detail, they found minuscule fluctuations in temperature, only about 1 part in 100,000. These tiny irregularities were not noise. They were the seeds. They represent the earliest blueprints of structure in the universe. Regions slightly denser than their surroundings had stronger gravitational pull, drawing more matter toward them over time. These became the first clumps of gas, which grew into stars, then galaxies, and then the grand cosmic web that we see today. So those tiny differences, imprinted on the CMB nearly 14 billion years ago, are the fingerprints of our cosmic heritage. In the first fleeting fraction of a second after the Big Bang, something extraordinary happened. The universe, unimaginably hot and dense, underwent a burst of expansion so rapid and so vast that it changed the nature of everything that followed. This event is called cosmic inflation. It lasted only a tiny sliver of time, perhaps less than a trillionth of a second. But in that moment, the universe grew from smaller than an atom to the size of a grapefruit, or even larger. And though it was over almost as soon as it began, its fingerprints are found everywhere across the cosmos. Cosmic inflation was proposed to explain some puzzling features of our universe. Chief among them is uniformity. When we look deep into the sky at the cosmic microwave background, the afterglow of the Big Bang, we see that it is nearly the same temperature in every direction. This is strange, because according to the standard Big Bang model, before inflation was added, there simply hasn't been enough time for light, or any signal, to travel across the vast distances between opposite sides of the sky. In other words, these regions should be causally disconnected. They should not know anything about each other. And yet, they appear to be in perfect thermal balance. Inflation solves this by dramatically changing the early history of the universe. Before inflation, the observable universe was much smaller, and regions we now see as separated by billions of light years were close enough to exchange energy and come into equilibrium. Then, during inflation, space expanded so quickly that these once connected regions were torn apart, carried beyond each other's horizons. They still bear the imprint of their past interactions, and this is why we see such remarkable uniformity today. But inflation provides more than just an explanation for uniformity. It also predicts something quite subtle: tiny variations in density. Perfect uniformity would give rise to a featureless universe. Stars, galaxies, and planets would never form. Inflation suggests that during this rapid expansion, quantum fluctuations, uncertainties inherent in space itself, were stretched from the smallest scales to cosmic proportions. These fluctuations became the seeds from which all structure grew. The evidence for this comes from the patterns we observe in the cosmic microwave background. Sensitive instruments like those aboard the WMP and Planck satellites have measured minute temperature differences across the sky, differences of just 1 part in 100,000. These tiny hot and cold spots align almost exactly with what inflationary theory predicts. Where space was slightly denser, gravity eventually pulled more matter in, forming the knots and filaments we now see in the cosmic web of galaxies. Where it was less dense, voids emerged. Another mystery that inflation aimed to solve is the flatness of the universe. If space had even a slight curve at the beginning, that curvature would have grown over time, leading to either a closed universe that would eventually collapse, or an open one that would expand too quickly for galaxies to form. Yet observations tell us that the geometry of space, on the largest scales, is remarkably flat. Inflation explains this too, just as a small patch of a balloon appears flat when viewed up close. Inflation stretched out any initial curvature, leaving behind a universe that appears flat across vast distances. The idea of inflation might seem almost too radical to accept, but its elegance lies in how it ties so many threads together. It takes a universe born from quantum uncertainty and stretches it to classical proportions. It explains the remarkable smoothness of the sky, the subtle imperfections that give rise to us, and the large-scale geometry of space itself. Yet inflation is more than a solution to a list of problems. It opens a gateway into deeper questions. If inflation happened once, might it happen again? Some extensions of the theory suggest that our universe is just one bubble in a frothing sea of inflationary expansion, with other bubbles forming their own universes, perhaps each with different physical laws. This brings us to the edge of the known and into the realm of the multiverse. Cosmic inflation stands as one of the most profound ideas in modern cosmology. It takes us back to a moment unimaginably close to the beginning, and offers a mechanism by which the structure, shape, and very possibility of the universe came into being. It links the physics of the very small, quantum fields, with the physics of the unimaginably large. And though it lasts only the briefest instant, its echo is heard across all of time. When we gaze into the depths of space, we are not just looking outward, but backward, back to a moment when time itself had barely begun. The smoothness of the sky, the ripples in the cosmic microwave background, the galaxies scattered like islands in a cosmic ocean, all are whispered reminders of that moment of inflation, a whisper carved into the fabric of space itself. In the beginning, there was no light, no matter, no time as we know it, only a seething, incomprehensible density. The universe, vast and ancient now, began in an instant of unimaginable energy. In the first sliver of time, far smaller than 1 second, physics, as we understand it, begins to unfold. This earliest moment is called the Planck epoch. It lasted until the universe was about 1/10 million trillionth of a second old. During this time, all of the fundamental forces we observe today, gravity, electromagnetism, the strong and weak nuclear forces, were possibly united into a single force, a force unlike anything we can measure or recreate. Describing this state requires a theory that merges general relativity with quantum mechanics. And while such a theory remains incomplete, what we do know allows us a glimpse, a poetic sketch, into these primal moments. At this scale, space and time were not yet distinguishable in any meaningful way. The universe was a quantum phone, a turbulent sea of fluctuations in energy and geometry at the smallest possible scale, the Planck scale. The fabric of space-time was churning and unstable, punctuated by bubbles and distortions, like the surface of boiling water magnified trillions upon trillions of times. Temperature and density were both infinite, at least in the language of equations, a singularity not just of matter, but of understanding. As the universe expanded and cooled, it entered the grand unification epoch, a period that might have lasted until about 1/10,000 trillionth of a second after the Big Bang. During this time, gravity had already split off as a distinct force, leaving the strong nuclear force, electromagnetic force, and weak nuclear force potentially acting as one. This theoretical stage, suggested by grand unified theories, hints at a symmetry more elegant and refined than anything we see in nature today. Yet symmetry rarely lasts. As expansion continued, tiny differences began to emerge. Minute energy fluctuations gained significance as temperatures fell. The unified force began to fragment under the cooling weight of time. The strong nuclear force was the next to break away, freezing into its own distinct role by around 10 trillionths of a second. This force would later hold protons and neutrons tightly together in atomic nuclei. But in these moments, it simply marked a great divide in the universe's evolution. The separation of forces was not just a passive process. As symmetries broke, energy was released. Violent and relentless, this release may have given rise to inflation, a colossal expansion that blew space apart far faster than the speed of light, not violating relativity, but reshaping the landscape of the cosmos. During this exponential surge, quantum fluctuations were stretched across the stars, becoming the seeds for every galaxy and cluster to come. Next came the electro-weak epoch. This phase began as the universe reached around 1/10 billionth of a second. During this time, the electromagnetic force and the weak nuclear force still danced together as one. But soon, a final symmetry would break, and again, the universe would shift irrevocably. The weak nuclear force, responsible for radioactive decay and the inner workings of the sun, would separate from the electromagnetic force, which would come to govern light and magnetism. It may seem a quiet change now, but these separations sculpted the path of cosmic history. By the end of the first second, the four fundamental forces had settled into their current forms. Gravity, always weak but far-reaching. The strong nuclear force, fierce but confined within atomic nuclei. The electromagnetic force, weaving together light and charge. And the weak force, subtle but vital for the transformation of elements in stars. As each force broke away, the universe became more intricate. Complexity followed the cooling, like mist following dusk. Before 1 second had passed, the foundations had been laid. The shape of tomorrow was drawn from the physics of these fleeting instants. Matter was not yet formed in the usual sense. Quarks and leptons were still seething in energy-rich oceans, but the rules of the game were set. These forces would go on to govern the binding of protons and neutrons, the birth of light atoms, the glowing of stars, the turning of galaxies. Each force a note in the symphony of existence, and the universe, once a single unfathomable point, was already becoming space itself, stretching, cooling, unfolding. That these processes occurred in a time so short we struggle to imagine it, speaks to the astonishing precision of reality. The deepest truths of nature took shape in moments that passed, before any particle could even settle into structure. If the forces had split differently, if their strengths had varied even slightly, the universe we know, and life within it, may never have existed. We look back at this origin not with absolute certainty, but with awe. Through mathematics, particles and light captured from the distant past, we piece together a narrative that continues to unfold. A universe that, even in its first whisper of time, was already writing the story of everything to come. When we look up at the vast night sky, dotted with stars and threaded with the faint glow of distant galaxies, we are seeing only a fraction of what truly exists. The cosmos, as beautiful and luminous as it appears, hides a profound mystery. A missing mass, an invisible presence, something that does not shine, does not absorb or emit light, yet reveals itself through gravity. We call it dark matter, and its fingerprint is most clearly seen in the way galaxies spin. In the 1970s, astronomers studying spiral galaxies made a discovery that would shake the foundations of cosmology. Vera Rubin and her colleagues began mapping the rotation speeds of stars as they orbited the centers of galaxies. According to the laws of Newtonian dynamics, which had long governed our understanding of motion, stars farther from the galactic center should move more slowly than stars closer in. The outermost stars, feeling less gravitational pull, should gradually slip behind. But this wasn't what Rubin observed. Instead, the stars at the edges of galaxies weren't slowing down at all. They were moving just as fast as stars near the center. The rotation curves, plots of orbital velocity against distance, were flat. It was as though there was an enormous reservoir of matter surrounding each galaxy, imparting additional gravitational pull. Yet this matter emitted no light. It could not be seen directly. Whatever it was, it had to be there. The galaxy rotation curves left little room for doubt. Over the decades, this phenomenon has been confirmed across the cosmos. From dwarf galaxies to giant clusters, the same pattern emerges. Luminous matter, stars, gas, and dust, accounts for only a fraction of the gravitational force needed to hold these systems together. Dark matter does not interact with light or the electromagnetic force. It passes through ordinary matter with almost no effect. Yet it influences the fabric of space profoundly. It asserts itself through gravity, shaping the structure of the universe on the grandest scales. In the early universe, just after the Big Bang, matter was almost evenly spread. There were tiny fluctuations, variations in density as small as 1 part in 100,000. These slight differences acted as the seeds from which all cosmic structures grew. But ordinary matter alone could not have formed galaxies as quickly as we see them emerge in simulations or observations. It would have taken too long, smoothing over the delicate patterns in the cosmic microwave background. Dark matter changes this story. It decouples from radiation earlier than baryonic matter, meaning it began collapsing into clumps sooner. These clumps became gravitational wells, drawing in gas and dust. Stars were born, and galaxies formed around these invisible scaffolds. Without dark matter, the large-scale structure of the universe, the cosmic web of filaments, nodes, and voids, wouldn't look the way it does. It provides the unseen framework that guides the visible. Galaxy clusters offer further evidence. They are the largest bound structures in the universe, containing hundreds or thousands of galaxies, along with hot gas and, crucially, dark matter. When we look at how galaxies move within these clusters, once again, there's far more mass than meets the eye. X-ray measurements of the hot intracluster gas confirm this. The gas alone has too much energy to be held in by the visible gravitational pull. Something invisible must be anchoring it. Gravitational lensing gives us yet another window into this elusive substance. Light from distant galaxies bends as it passes near massive objects, much like light refracts through a lens. When we observe strong lensing effects, rings, arcs, and distortions, we can map the total mass of the foreground object. Time and time again, these maps show far more mass than we can account for with stars and gas. Dark matter is inferred through the warping of space itself. All these lines of evidence converge. From galaxy rotation curves to cluster dynamics, from lensing to cosmological simulations, dark matter is not a speculative addition. It is a necessary piece of a larger puzzle. And yet, we still don't know what it is. The leading candidates are hypothetical particles, created in the furnace of the early universe. They are cold, meaning they move slowly, and interact only through gravity and perhaps the weak nuclear force. WIMPs, axions, sterile neutrinos. These names carry our hopes for a detection. Experiments buried deep underground and telescopes scanning the skies search for signs. So far, dark matter has remained hidden. Still, its impact is profound. It sculpts the galaxies, binds clusters, and defines the skeletal framework of the universe. Without it, the cosmos would be a very different place, perhaps flat and featureless, a grey fog of gas stretching from horizon to horizon. Instead, we have structure, richness, and the complexity needed for stars to shine, for planets to form, and for life to emerge. Dark matter is the shadow architecture of the universe, a silent force that holds the galaxies in its grasp. Though invisible, its presence is felt in every corner of the cosmos. And as we peer ever deeper into space, we are not only mapping the visible stars and galaxies, we are also tracing the outlines of something older, colder, and darker, waiting, still concealed, just beyond the reach of light. The story of the universe begins not with a gentle unfolding, but with a singularity, an almost unimaginable point of infinite density and energy. From that moment, nearly 14 billion years ago, time and space began their expansion. One of the most profound questions in science has been how to measure the age of this cosmos, this grand unfolding of matter and energy. The most direct method lies in observing the expansion of the universe itself. Edwin Hubble's discoveries in the early 20th century revealed that galaxies are not stationary, but drifting apart. The farther away a galaxy is, the faster it appears to be moving. This observation, called redshift, indicates that the universe is expanding uniformly in all directions. If we trace this expansion backwards, we find a point in time when all matter would have been compressed into one place. This is the birth of the universe. By precisely measuring the rate of expansion today, the Hubble constant, we can calculate how long this expansion has been occurring. But measuring the Hubble constant is not as simple as it might seem. Different approaches produce slightly different values. Some rely on observing nearby celestial objects, like Cepheid variables and Type 1a supernovae. Others use data from the cosmic microwave background radiation, a faint glow left over from the early universe. This ancient light, observed by satellites like Planck and WMA, carries an imprint of the universe as it was nearly 400,000 years after the Big Bang. By analyzing its tiny fluctuations in temperature, scientists can deduce the content and geometry of the cosmos. From there, they can infer how fast the universe has expanded over time and arrive at an age. Despite the differing methods, the results all point to a universe that is roughly 13.8 billion years old. It is a remarkable convergence, a testament to the power and precision of modern cosmology. The age derived from expansion measurements agrees very closely with the predictions made by the Big Bang theory. And that agreement is strengthened by other lines of evidence. Consider the oldest known stars. Located in ancient globular clusters, some of them seem nearly as old as the universe itself. Their ages are estimated by modeling the way stars evolve over time, burning through hydrogen and producing helium. By observing their brightness and temperature, astronomers construct what is called a Hertzsprung-Russell diagram, a kind of stellar family tree. The result is clear. The stars in these clusters are old, but not older than the universe itself. That may sound obvious, but it's crucial. If our estimate for the age of the universe had been too low, we would find stars older than the cosmos they inhabit. That would pose a serious problem, but we don't. The pieces fit. Another confirmation comes from the abundance of light elements. In the first few minutes after the Big Bang, the universe was hot and dense enough for nuclear reactions to occur. This process, known as Big Bang nucleosynthesis, created predictable amounts of hydrogen, helium, and trace quantities of lithium. The precise ratios depend on the conditions in the early universe, including its age and rate of expansion. Today, we measure these elements in the oldest regions of the cosmos, and once again, the predictions match observation. The helium fraction, in particular, lines up exactly with what the Big Bang theory predicts for a universe of this age. Then there is the cosmic microwave background. When we peer into this all-encompassing fog of ancient light, we are witnessing a snapshot of the universe when it was less than 500,000 years old. The tiny temperature variations across the sky reveal information about the composition and structure of the early cosmos. From these patterns, cosmologists extract the values for critical parameters, including the rate of expansion, the density of matter and energy, and the age of the universe itself. The degree of precision is astonishing. Arcane signals encoded in ancient photons tell us that the universe is 13,800,000,000 years old, give or take a few tens of millions. Still, small disagreements remain. While measurements of the cosmic background suggest one value for the Hubble constant, local observations of supernovae suggest a slightly higher one. This tension has led scientists to consider whether we are missing something fundamental. Is there a new particle or force which subtly alters the expansion rate? Could dark energy behave differently than we assume? Or perhaps we simply have not yet accounted for all the complexities in our models. These are questions at the frontier, but they do not undermine the broader picture. Across multiple independent lines of evidence, stellar evolution, cosmic background radiation, expansion measurements, and primordial element ratios, we find a consistent story. A universe that erupted from a hot, dense origin, expanded and cooled, and has been evolving for nearly 14 billion years. The age of the universe is not just a number, it's a measure of time itself. Since the beginning, a reckoning of all the moments that have passed since everything began. It defines the lives of stars, the cycles of galaxies, and the arc of cosmic history. And out of that vast immensity, we find ourselves here, in a quiet corner of a spiral galaxy, tracing the paths of ancient light back to the dawn of time. When we look up at the night sky, we are not looking into space as it is now. We are looking back in time. The light from distant galaxies takes billions of years to reach us. The farther away an object is, the older the light we see. This leads to an extraordinary idea. There is a limit to how far we can see, not because there is a wall or an edge, but because light has a finite speed and the universe has a finite age. That boundary is called the observable universe. It defines the region of space from which light has had time to reach us since the beginning of the cosmos. Beyond this region, the universe may continue, perhaps infinitely, but we cannot see it. Not now, and perhaps not ever. The observable universe is bounded not by a physical edge, but by time itself. The light horizon is another name for this limit. In today's universe, that horizon defines a sphere with a radius of about 46 billion light years. That might seem counterintuitive, since the universe is thought to be around 13.8 billion years old. The reason the distance is greater than 13.8 billion light years is due to the expansion of space. As light travels toward us, the fabric of space itself stretches. It carries galaxies further away as light moves through the void. Space is not static. It has been expanding since the Big Bang. That expansion means that the most distant galaxies we can observe were once much closer. They emitted their light long ago when the universe was much younger. But as that light traveled, the universe grew and the galaxies moved further away. What began as a short journey turned into a very long one. Light that has been traveling for over 13 billion years now reaches us from a place that is far more than 13 billion light years away. This stretching of space also means that much of the universe is receding from us. Distant galaxies are moving away faster than nearby ones. This movement is not through space, but of space. It is expansion in its purest sense. And because of this, there are galaxies moving away from us so quickly that their light will never reach us, even if we wait forever. Those regions lie beyond our cosmic event horizon. They are lost to us, not because they do not exist, but because cause and effect cannot bridge the gap between us. The light horizon and the observable universe tell us something profound. There are limits, absolute physical limits, to what we can know. Even with the most powerful telescopes, there will always be more beyond our view. The observable universe contains perhaps 2 trillion galaxies. Each galaxy may hold hundreds of billions of stars. Yet all of this cosmic abundance is only a fraction of what might exist. The shape and structure of the observable universe also give us clues about the whole. The cosmos appears the same in all directions, uniform and isotropic. That suggests a larger symmetry, even beyond what we can see. But we cannot be certain. Whether the universe is infinite or simply much larger than the observable patch, it is a question we may never answer. Cosmic expansion does more than limit our view. It has shaped the course of cosmic history. In the early universe, matter was concentrated, hot and dense. As space expanded, it cooled, allowing atoms to form and light to travel freely. Structures grew, first clouds of hydrogen, then stars, then galaxies. Without expansion, the universe would never have evolved the way it has. There would be no time, no place, no conditions for complexity to emerge. Even now, the expansion continues, and it is not slowing down. In fact, due to a mysterious force called dark energy, the universe is accelerating. This has startling implications. Over vast spans of time, more galaxies will pass beyond our horizon. The observable universe will shrink in content, not in size, as fewer and fewer galaxies remain within reach. Eventually, only our local group of galaxies may remain visible, a lonely island in an ever-darkening sea of space. But for now, the light continues to flow in. Each photon that reaches Earth from a distant quasar or galaxy carries a message from the past, tiny, ancient pulses from a much younger universe. Gathered by our telescopes, they allow us to reconstruct the grand story of cosmic evolution. The observable universe is a silent frontier, not a limit of the universe itself, but of our knowledge. Yet within that limit, we have discovered wonders. We have traced the echoes of the Big Bang, mapped the mass of galaxies, and seen light from merely the beginning of time. In doing so, we have learned that the universe is not just vast, but interconnected. Every ray of light, every particle of matter, part of a history billions of years in the making. And perhaps, through quiet understanding of what we can observe, we come closer to grasping the immensity of what we cannot. In the cold vastness of space, just 3 degrees above absolute zero, there is a whisper, a background glow washing over the entire sky in all directions. This faint radiation is the afterglow of the Big Bang, a relic from a time when the universe itself was only a few 100,000 years old. Encoded in that glow is a story of beginnings, temperature, density, and time. To test the Big Bang theory, scientists needed to read that story. They needed to capture the light from the earliest moments of existence and analyze it with unbearable precision. That journey began in earnest with the launch of a satellite known as CHOPE, the Cosmic Background Explorer. It left Earth in 1989 with a clear goal: to measure the cosmic microwave background radiation, the CMB. This radiation had already been discovered decades earlier by Arno Penzias and Robert Wilson in 1965. Their accidental detection of an ever-present isotropic hum in their radio antenna provided the first solid observational evidence of the Big Bang. But it was only the beginning. CHOPE's mission was to go further, to measure the exact spectrum of the radiation and map faint variations in temperature across the sky. These temperature fluctuations, although extremely slight, just 1 part in 100,000, were crucial. They represented differences in density in the early universe, tiny ripples from which galaxies would later grow. If the Big Bang theory was correct, those ripples had to be there. The specifics of their distribution would tell us how matter clumped together, how cosmic structure formed, and whether the theory held. CHOPE delivered. It confirmed that the spectrum of the cosmic microwave background matched that expected from a nearly perfect black body. In other words, the radiation we see today really did come from a hot, dense early state, a universe in an almost perfect thermal equilibrium. Even more thrilling, COB unveiled those first-minute anisotropies. Soft spots and warm spots stretched across the sky. It was like hearing the heartbeat of the infant cosmos. The results earned John Mather and George Smoot the Nobel Prize in Physics in 2006. The first note of the symphony had been heard. But COB's resolution was relatively coarse. The initial map was like a blurry fingerprint. To decode the fine details, we needed something more powerful. In 2001, the Wilkinson Microwave Anisotropy Probe, or WMAP, was launched. It orbited a point in space known as Lagrange Point 2, a quiet, gravitationally balanced region beyond the Moon. There, WMAP could observe the cosmos undisturbed by the warmth and radiation of Earth. Over the course of 9 years, it created a map of the CMB with over 45 times the resolution of CHOPE. WMAP's data revealed not only the detailed structure of temperature fluctuations, but also gave us a precise measure of the universe's age, about 13.8 billion years. It also told us the composition of the cosmos, roughly 5% ordinary matter, 25% dark matter, and 70% dark energy. These were not abstract concepts. They emerged from the geometry and energy density encoded in the microwave background. The Big Bang theory, with inflationary expansion in its earliest moments, passed every test it faced. But science is ever in pursuit of perfection. And so came Planck. Launched by the European Space Agency in 2009, the Planck satellite became the most sensitive instrument ever designed for study in the CMB. Over 4 years, it mapped the sky at even higher resolution and across more frequencies. Planck's detectors were so sensitive, they could distinguish temperature differences of a few millionths of a degree. What it found was a beautifully intricate structure of fluctuations, patterns that told the story of the very earliest instance, when quantum fluctuations were stretched across the nascent universe by inflation. By measuring the polarization of the microwave background, Planck gave insights into the timeline of cosmic reionization, the period when the first stars and galaxies lit up the universe again, clearing away the cosmic fog that followed the recombination era. And in its readings, Planck made one thing abundantly clear: the universe is spatially flat, supporting key predictions of inflationary models tied to the Big Bang scenario. Individually and together, These missions, COBE, WMA, and Planck, transformed our understanding of the cosmos. They did not merely support the Big Bang theory, they charted its fingerprints across the heavens. The data showed again and again that our universe began as an incredibly dense, hot fireball that has expanded and cooled over almost 14 billion years. The precision of these modern observations was astonishing. The CMB, once a foggy echo, now stands as the most thoroughly studied light in all of astronomy. The older it is, the more clearly we see it. We find the clearest confirmation that the Big Bang was real. But from a moment of unimaginable compression and temperature, a universe arose, governed by laws we are only beginning to understand. The satellites have now gone silent. Their missions are complete, but their data echoes forward. And as we look up into a sky saturated with ancient radiation, it is humbling to realize that the cosmos revealed its origins not in thunderous signals, but in the gentle hush of microwaves, from a time when there were no stars, no galaxies, no Earth, only energy, space, and the possibility of becoming. At the smallest scales imaginable, far beneath the familiar world of atoms and molecules, lies a strange and beautiful realm governed by the laws of quantum mechanics. These laws do not describe certainty, but probability. They tell us not where something is, but where it might be. On large scales, this seems almost irrelevant, yet our modern understanding of the universe, its birth and its structure, depends on this deep quantum uncertainty. To see this, we must go back to the beginning. Not the first moment of the Big Bang exactly, but a fraction of a second later. The universe, still immensely hot and dense, underwent a sudden and astonishing transformation. In less than a trillionth of a second, the universe expanded exponentially, stretching from subatomic scales to macroscopic size. This smooth but incredibly rapid inflation smoothed out the irregularities of the early universe. It made the cosmos, on large scales, astonishingly uniform. But no process, not even inflation, can erase the fluctuations that arise from quantum mechanics. During inflation, empty space was not truly empty. It was seething with particles and antiparticles flickering into and out of existence, as allowed by the uncertainty principle. These quantum fluctuations were present everywhere. They were microscopic, inherent to the very fabric of space and time. And yet, through the stretching power of inflation, these tiny imprints in the quantum field were inflated to cosmic proportions. These fluctuations were made permanent. Once stretched far beyond the subatomic realm, gravity amplified them. Regions slightly denser than their surroundings began to pull in more matter. Over hundreds of millions of years, these small differences grew. Galaxies, clusters, and vast cosmic filaments formed, all from initial quantum ripples. Without quantum mechanics, there would have been no structure in the universe at all. The fingerprints of these early fluctuations remain today. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see slight variations in temperature. These are the echoes of ancient quantum fluctuations, frozen into the sky. They tell a story that spans across 13.8 billion years. A story that begins not with chaos, but with orderly quantum rules. This insight connects the smallest known scales to the largest. Quantum fields, which pervade all of space, underpin the behavior of particles in high-energy physics. But during inflation, these same fields played a new role, shaping the cosmos itself. The inflaton, a hypothesized scalar field, is thought to have driven inflation. Unlike familiar particles such as electrons or quarks, the inflatum is not observed directly, but its dynamics, governed by quantum principles, helped power the rapid expansion in the early moments of the universe. Quantum theory also explains how these fluctuations arose. Even in their lowest energy states, quantum fields cannot be perfectly still. They are always in motion, always uncertain. This uncertainty leads to fluctuations in energy density, which, under rapid inflation, translate into tiny differences in temperature and structure across the expanding universe. These differences were subtle but crucial. They determined where matter would gather over time and where it would not. It is astonishing to consider that everything we see today, stars, galaxies, planets, even ourselves, owes its existence to an elemental randomness rooted in quantum mechanics. Without these fluctuations, the universe might have remained smooth and featureless. There would have been no stars to shine, no planets to orbit them, and no life to ponder its origin. Modern physics continues to probe this connection. Quantum field theory and general relativity, the two great pillars of 20th century physics, are not entirely reconciled. Inflation lies at the edge of both domains. It requires a quantum description of gravity, something we do not yet possess, and so, understanding quantum fluctuations during inflation is one of the most promising pathways to a theory of quantum gravity. It may lead to deeper insights into how time and space themselves emerged from a more fundamental reality. In this way, the story of the universe is also the story of quantum physics, from the randomness of particles to the order of galaxies. The laws that govern the microscopic realm have left an indelible mark across the heavens. They link the spooky strangeness of quantum entanglement to the motions of distant galaxy clusters. They connect the soft glow of the night sky to events that once occurred within a volume far smaller than a proton. This is one of the great triumphs of cosmology, that by observing the universe on the grandest scales, we are also performing a kind of particle physics. The sky itself becomes a laboratory. Each photon of ancient light carries the signature of quantum fluctuations stretched across a fledgling universe. And as we measure them ever more precisely, we uncover more of the universe's origin story. In the silence of the vast cosmic web, every galaxy whispers of inflation. Every cluster recalls the brief moment when space itself surged outward faster than light, and every structure preserves the trace of those first quantum tremors. Through inflation, through quantum mechanics, the invisible becomes visible. And so, at the foundation of our modern understanding of the cosmos, we find not only the grand arcs of gravity and energy, but also the soft, uncertain flickering of quantum fields, writing the early chapters of the universe in probabilities, not certainties. From this delicate balance arose all that we see. In the final pages of our current understanding of the cosmos, a quiet mystery arises from the edges of the known. It begins with a question born not from observation, but from mathematics and the inescapable logic of physics. If the Big Bang gave rise to our universe, could it not give rise to many others? Entire other realms, each with their own stars, galaxies, perhaps even laws of physics. This is the curious idea of the multiverse. It is not a single idea, but a family of ideas braided together by theories in cosmology, quantum mechanics, and string theory. These models suggest that our universe, vast though it is, might be like a bubble in a much larger cosmic ocean. And in that ocean, other bubbles may form, expand, and fade. Each one is a universe, born from its own Big Bang, each with its own version of reality. Inflation theory, which explains the uniformity of the cosmic microwave background and the large-scale structure of space, provides one such path toward the multiverse. It proposes that just after our Big Bang, the universe expanded faster than the speed of light in a fraction of a second. But inflation may not be a one-time event. Some versions of this theory suggest that inflation is eternal, continuing in distant parts of the cosmos, forever spawning disconnected regions like ours. These regions are what physicists call pocket universes. Each pocket may contain different values of fundamental constants. Some might have stronger gravity, others might not allow the formation of atoms at all. Most would be lifeless, cold, and dark. But among the near-infinite possibilities, it is statistically likely that at least one would look like ours. Perhaps even many. Maybe life, or something like it, flourishes in more than just our corner of existence. The quantum world also suggests a strange kind of multiverse. In quantum mechanics, particles do not have definite paths. Instead, they exist as probabilities until measured. One interpretation of this, the many worlds interpretation, claims that every possible outcome actually occurs. The universe splits, not in space, but in information. In one split, the particle travels left. In another, it travels right. Your history, your decisions, even your thoughts, may echo in unfathomably many branches of reality. These versions of the multiverse are not yet testable. They stretch our imagination, and for now, they hover on the edge of what science can touch. Yet other ideas may offer paths toward evidence. In the realm of string theory, the very fabric of the universe is composed not of particles, but of minuscule vibrating strings of energy. This theory requires more than the 3 dimensions of space and 1 of time that we experience. It predicts the existence of as many as 11 dimensions. The reason why we don't perceive them is that they may be curled up at unimaginably small scales, like a sheet of paper rolled so tightly it appears as a line. Within string theory's complex geometries, different configurations may yield entirely different physical laws. Each configuration can describe a unique universe, and the landscape of possibilities is as vast as it is varied. The result is a multiverse of extraordinary diversity, each universe the result of one possible shape that the curled-up dimensions might take. Some scientists speak of a string landscape, a theoretical patchwork of solutions that allow different universes to emerge. In this view, the universe we see, stars, galaxies, ourselves, is simply one particular arrangement amid a cosmic library of alternatives. We find ourselves here because it is one of the rare combinations that permits the formation of atoms, chemistry, biology, and thought. There is another possibility, equally profound, that the laws of physics in our universe are not unique, but part of a broader ecology. The constants we measure may appear finely tuned for life, but in a multiverse, this becomes less surprising. Life arises only in those universes where it can. So we look out from one of the rare islands of habitability, while most of the cosmic ocean remains silent. Of course, there is caution here. The multiverse, if true, may never be fully observable. Light from other universes might never reach us, and space itself may separate them more completely and even the vast gaps between stars. The multiverse might remain forever beyond the horizon of empirical proof. And yet, the idea shapes how we think about the cosmos. It stretches the limits of our models and tests the power of our mathematics. It reminds us that science is not just about explaining what is, but imagining what might be. In the beginning, we thought our world was the center of everything. Then, we discovered planets, stars, galaxies, grains of dust in a vast sea. Now, we stand on another edge, wondering whether our entire universe might be just one grain among countless others. We may never reach these other worlds, but asking the question changes us. It expands the frame through which we view everything, including ourselves. For in the search for meaning in the stars, we sometimes rediscover the miracle of standing here at all. The Big Bang Theory describes a beginning, a moment when space and time, energy and matter, all emerged from an unimaginably dense and hot singularity. For some, this is a scientific model supported by observation and mathematics. For others, it is a story that echoes ancient myths, laying bare humanity's timeless yearning to know where we come from and why we are here. The idea that the universe had a beginning carries profound philosophical implications. If time itself began nearly 14 billion years ago, then what came before becomes a meaningless question. There was no before in any physical sense. The arrow of time, which we experience every day, had its roots in this singular event. It was not merely a moment in time, it was the beginning of time itself. This stretches our imagination and challenges our understanding of causality. For centuries, philosophers and theologians have pondered the nature of existence. They have asked what it means for the universe to exist, and whether something as vast and intricate as the cosmos could arise from nothing. The Big Bang does not give us a definitive answer, but it paints a vivid picture of a universe that is dynamic and evolving, driven by physical laws that we are only beginning to comprehend. In ancient cultures, origin stories were woven into the fabric of belief. They gave people a place in the cosmos, a purpose, and a connection to something larger than themselves. These creation myths varied, but many shared a common thread: the transformation from chaos to order. In some traditions, the universe was born from the body of a deity, or uttered into existence by a word. In others, it was formed from an egg, a void, or a cosmic explosion. It is striking how the scientific narrative of the Big Bang mirrors these themes. An initial moment of profound energy and density unfolds into complexity, structure, and eventually consciousness. Stars form from collapsing clouds of gas. Plant matter evolves over generations into sentient beings. And now, these beings, us, look back across time and space to trace the path of their own origin. Some see in the Big Bang a confirmation of spiritual ideas, interpreting the beginning of the universe as the moment of creation. Others feel it replaces the need for a divine cause, showing that the universe can develop according to physical laws alone. In either case, the spiritual dimensions are impossible but to ignore. The fact that the universe had a beginning challenges the long-held belief in an eternal, unchanging cosmos. It forces us to reckon with the astonishing possibility that the universe is not just a place we inhabit, but something that has a history, a trajectory, and perhaps even a fate. The question of why there is something rather than nothing remains beyond the reach of experiment. The Big Bang describes how the universe began, but it does not explain why it began. Some physicists explore theories involving quantum fluctuations or multiverses, suggesting that universes may arise from the shifting vacuum of space itself. But these ideas are speculative and, for now, untestable. They belong to the frontier, where science brushes against the philosophical. Existential questions naturally arise. If the universe had a beginning, does it have a purpose? If the laws of physics are the same everywhere, what does that say about our place within them? Are we a product of necessity, of chance, or of something deeper? The Big Bang does not answer these questions directly, but it does transform them. It takes them from abstract musings and roots them in a cosmic narrative that we can observe, study, and understand. The theological interpretations vary. Some religious thinkers embrace the Big Bang as evidence that the universe was created, aligning the scientific timeline with scriptural accounts of cosmic origin. Others maintain that the divine transcends physical models and cannot be confined to equations or data. Still others view science and faith as addressing different kinds of truth, one concerned with mechanisms, the other with meaning. There is room in the discussion for all. The idea that, from a seething fireball of energy and particles, galaxies would come to rotate, stars would burn, and life would emerge, is simply staggering. That we find ourselves here, capable of pondering the origin of the cosmos, is a wonder in itself. We are a part of this unfolding story, not separate from it, but born from it. In the end, the Big Bang ties us to the fabric of the cosmos in a deeply intimate way. Every atom in our bodies was forged in the heart of stars that themselves owe their existence to the conditions set in motion by that first instant. We are the product of an ancient expansion, written in the language of hydrogen and helium, gravity and light. Whether one sees the Big Bang as the handiwork of a creator or as the elegant outcome of physical law, it deepens the mystery rather than resolving it. It opens the door to questions that are as old as thought itself, but now informed by the insights of science. In striving to understand the birth of the universe, we glimpse something of our own beginnings. And in that glimpse, we find wonder, humility, and a renewed sense of our place in the vast and extraordinary cosmos.